Good day, everyone. This video is to explain what it means to complexify a function, how to do it, and why we do it. So first of all, we have a little definition here. Complexifying a function means that we represent a real valued function as the real or imaginary part of some complex function. Now, a simple example is the cosine of x can be represented as the real part of this complex exponential e to the ix, where I is the square root of -1. Now, where this comes from is Euler's identity, which states the following. It says that e to the ix is cosine of x plus I sine of x. So indeed, the real part of this is the cosine of x. Now, to give you an example of how we use this, say we want to integrate the cosine of x. The integral of the cosine of x dx, well, we know that's the sine of x. And there's no need to complexify this function to do this example, as it's easy to integrate cosine. But we want to kind of demonstrate the process anyway. So if I decide I want to integrate this exponential instead of integrating this, what I would do is to find the integral of the cosine of x, we would say this. The integral of the cosine of x is equal to the real part of the integral of e to the ix. So let's see that that works. Well, the integral of e to the ix, that's equal to e to the ix over I, which can be written as minus I e to the ix. Okay, so we've done the integration. And now we take the real part of this. So first of all, minus I times e to the ix is times cosine of x plus I sine of x. That's equal to minus I times cosine of x. Then I have I squared, which is -1, plus sine x. And now we take the real part of this, and the real part of this is the sine of x, which is correct. So the real part of the above is sine x. Okay, well, let's look at an example of where complexifying the function actually helps and saves time and work. We're going to integrate the following. The integral of e to the x times cosine of x dx. Now, from your calculus course, to do this integral, you would have to integrate by parts. And after you do that, you're going to end up with an e to the x sine of x. So you have to integrate by parts a second time. And then after that, you're going to have to do some additional algebra, moving everything to one side before you can finally figure out what that integral is. Let's complexify this function and see how easy it is to integrate. So to complexify e dx cosine of x, e dx cosine of x, that's the real part of e to the x, e to the ix. And so what I'm going to do is integrate this instead, and then take the real part. So e dx, that's going to be e to the 1 plus I x dx. So here's the idea. Instead of having to integrate this, we integrate that, which is Easy. It's e to the 1 plus ix, which I'm going to rewrite like this, e to the x, e to the ix, divided by 1 plus I. So we're done with the integration. Again, this will require a significant amount of work. We're done. However, we have to take the real part of this. Now, to take the real part of this, I'm going to pull out that e to the x for a moment. And this 1 over 1 plus I, we will multiply top and bottom by the complex conjugate. And then we're going to take e to the ix, which is cosine x plus I sine x. You want to take the real part of this. So we're using Euler's identity to rewrite e to the ix this way. And this 1 over 1 plus I, I'm doing this. Now, 1 plus I times 1 minus I, that's equal to 2. So I had e to the x over 2. Now, when I multiply this out, I'm only going to be wanting the real part. And if you look at my video on complex numbers, you know what we could do is something called flow I instead of FOIL. We know the first and the last terms will generate the real part. So let me put it here, show you what we're doing. We're taking the real part of this. So I'm multiplying. I have this taken care of, this taken care of this. I got 1 minus I times this. So the real part is going to be the first. 1 times cosine of x. There it is. And the last is going to be minus I times I sine of x. That's going to be plus sine of x. And we are done. That is the integral of e to the x cosine of x. Okay. 1 plus I, 1 minus I is 1 squared plus 1 squared. That's 2. And when we multiply this out, since we just wanted the real part, we just took it. It's like multiplying two binomials. We took 1 times cosine minus I times plus I sine x. That's the correct answer. Now, let's take a look at solving a first-order linear ODE. So we need to solve y prime plus y, and let the input be cosine, and we're not going to specify the frequency. So we're going to just put omega there. Now, we want to find a solution to this using the integrating factor approach. Now, again, this is a first order linear ODE. And we're going to use the integrating factor approach to solve this. So, but what we're going to do, though, is complexify this input. And instead, we'll solve this problem. Y prime plus y is equal to e to the I omega x. The real part of this is our input. So we'll just solve this ODE, and at the end of the problem, take the real part. Now, our integrating factor is u of x. You might recall that is found by taking the e raised to the integral, the coefficient here, which is 1 dx. That's equal to e to the x. That's our integrating factor for this problem. We multiply both sides by that. And what happens when you do that, the left side will become the derivative of the product of your integrating factor times your unknown function, y of x. The derivative of that product. And the right side, we'll take this and multiply by this. So it's going to become e to the 1 plus I omega times x. I went ahead and combined these two exponents, these exponentials like this. Now, how do we isolate y of x? We integrate both sides. And when you integrate the left side, you're left with e to the x, yx, and we have to integrate e to the 1 plus I omega x dx. Of course, we have a constant of integration. Now again, right here, this looks like very similar to what we just integrated. This is easy to integrate. If you did not complexify, right here you would end up integrating a sinusoid times an exponential. You have to use integration by parts. So this integral, when you integrate this, is going to be e to the 1 plus I omega x divided by 1 plus I omega plus c. Now we will divide both sides by e to the x, which will give us y of x is the real part of, you divide by e to the x, that gets rid of this 1 right here, and you're left with e I omega over 1 plus I omega plus c e to the minus x. Pull this out because that's already real. Well, we take the real part of this and we're done. So this we're going to have to write as this 1 minus I omega, multiply top and bottom by the complex conjugate. When you multiply this by 1 minus I omega, the denominator becomes 1 plus omega squared. And of course, this part becomes cosine omega x plus I sine omega x. We're just about there. Plus c e to the minus x. So we want the real part of this. Well, we're going to use that flow I again. You're multiplying, this is like a binomial times a binomial. It's a complex number, right? So we take the first terms. So I am left with 1 over 1 plus omega squared cosine omega x. The last terms is going to, I have a minus I squared, which is plus omega sine omega x plus c e to the minus x. There is our general solution. This is y of x. Right there. Okay. And interesting, what we're noticing is because this ODE represents a low-pass filter, and we can see if you apply a sinusoid on the input, you get a sinusoid on the output, but the amplitude depends on your frequency. And as the frequency increases, your amplitude decreases. It's a low-pass filter. Well, one final example of complexifying a function is when we look at a second-order ODE, a second-order linear ODE. Here it goes. Y double prime plus Y. Well, this happens to be a harmonic oscillator. And let's apply cosine omega x on the input of that. So this is our final problem. This is a second order linear ODE. And this happens to be our harmonic oscillator. So what we want to do for this problem is we want to find a particular solution. Find a particular solution. And we will denote that particular solution as y sub p of x. And the way you find a particular solution, we use this method called undetermined coefficients. Method of undetermined coefficients, chapter 4 in the textbook. And if our input looks like this, we argue that the particular solution is going to have this form. It's going to be some A cosine omega x plus B sine omega x. So a particular solution is going to be of this form, but these coefficients need to be determined to find our solution. So you take this, plug it back into the equation, and solve for A and B. However, we are going to change the problem and complexify our input. Now that's not our input. The real part of that's our input, but we'll apply that and then take the real part of the answer. Let's do it. Now here, this being our input, the particular solution will have the form A e to the I omega x. So still called method of undetermined coefficients. Hey, we just got one coefficient we have to figure out now instead of two. And what you do is you take this and you plug it back in to the original ODE. Hey, I need a second derivative. Hey, I put y particular here. I need a second derivative. So let's do that. Y particular prime of x is equal to A I omega E I omega x. And we want the second derivative. That's going to be I squared. That's going to be A I squared is -1 omega squared e to the I omega x. And there's a minus here. See, the derivative of e to the u is e to the u prime, so I'm going to bring the I omega down here and multiply by this. I squared is -1, and you got minus omega squared. So now, plugging it in, I have my second derivative, which is, so we're going to take this and plug back into this. Actually, this one right here. So the second derivative is minus A omega squared E I omega x plus y, which is A E I omega x, is equal to E I omega x. What are we trying to do? We are trying to find A. Because once we know A, we've got our solution. The complex version of it. Well, here, what you do is you equate coefficients. I can combine these two, and what I'm going to have is A times 1 minus omega squared times e to the I omega x is equal to e to the I omega x. So the coefficient here, this has to be 1. A, 1 minus omega squared must be 1, and we have found A. A is equal to 1 over 1 minus omega squared. Okay. Well, so my particular solution is the real part of 1 over 1 minus omega squared times e to the I omega x. Well, this is nice. This is easy to find the real part. Here it is. It's equal to 1 over 1 minus omega squared cosine omega x. Okay. That is the particular solution for this second order ODE using complexifying functions. And if you're still not convinced of the value of this, suppose your input up here was a damped cosine. So suppose we have cosine omega x times e to the minus, x, some damped cosine. And what would be required to solve that? But complexifying this, it would be simply. Well, thank you very much for listening. And that's all we have for complexifying functions. Thank you.